Hello, class. This is Mr. Hunter, and this is your Newton Law Notes Part 3. This will be the end of the notes for Newton's laws because we're about to finish them up. So in Newton's first law, we talked about what can happen when the object stays at rest or in constant straight line speed. The forces are balanced or in equilibrium, which means my force net equals 0 newtons. So it's balanced on all sides. In the second law, Newton said, okay, well, what's happening when my forces are not balanced? What happens when I have an unbalanced force? And that causes the mass to accelerate. So in his third law, which is the final part of his summary of forces, it states for every force, there's an equal but opposite force. So when I'm sitting on the chair you're sitting in right now, um, there's a force pulling you down, gravity, and it's equal and opposite to the force of the chair pushing you up, and they're in opposite directions. So what this really means is forces and all forces happen in pairs. So they're action-reaction pairs. So let's take some examples. My first example, please excuse my horrible drawing, but oh well, it is what it is. So my first example is a bat is hitting a ball. And let's say that I hit that ball with the force of the bat, and according to Newton's third law, the ball is going to be equal but opposite direction, right? That makes sense. The bat's swinging to the left, the ball's coming to the right. So force of the bat equals negative the force of the ball. So that means that if I'm hitting the ball with 10 newtons of force, then the ball is hitting the bat with 10 newtons of force, just in the opposite direction. That's supposed to be a 10. For some reason, I wanted to draw an F. So that's just a simple real-life example of equal and opposite reaction pairs. But then let's say, what happens with, I'm angry that not a lot of my kids are doing the homework, so I punch a wall because I can't control my anger for some reason. Well, when I hit that wall, that's also an action-reaction pair. For every force is an equal and opposite force. So the force of my hand is going to equal opposite the force of the wall, because for every force there's an equal and opposite force. So once again, if I punch the wall with 10 newtons of force, the wall is punching me back with 10 newtons of force. Well, some of you hopefully are thinking, but probably not, but if you're thinking about baseball, well, you might ask, well, Mr. Hunter, if both of the objects are experiencing the same force, why does the baseball fly out into the field? Why don't they just like collide? They're the same force, and why don't they just both stop their motion immediately? Or if I'm punching a wall, why is it that my hand hurts after I hit the wall? Why does it they both just cancel each other out? And they don't cancel each other out because of Newton's second law. So if you scroll down further in the page, it says, so for every force, if every force has an equal and opposite force, why does the ball fly out into the field, or why does the hand hurt? And the reason is the objects have different mass, which means they have a different acceleration. Why? Because it goes back to Newton's second law. And as you're starting to see here, all of his laws are very intertwined. So F net equals ma, right? Well, if the bat and the ball are experiencing the same force, well, then the other side of this equation has to balance. Why? Because if they're both experiencing 10 newtons, right, the mass of the wall and the mass of my hand are both fixed. Since they're fixed, that means the acceleration is going to be different. In case of the wall, it has a huge mass, which means it's going to have a very small acceleration. In the case of the bat and the ball, right, the same force, but the bat has a huge mass compared to the ball, so it's going to accelerate a little bit. And the ball has a small mass, so it's going to have a huge acceleration comparatively. Why? Because they encounter the same forces. So because the objects have different masses, that's why they will accelerate differently, because they're hit with the same force. So when I talk about this in class, I'll talk about like hitting the wall. This also applies if you think about it with what we talked about with the physics of car crashes. Those cars, even though they have different momentums, they both will hit each other, and according to Newton's third law, they'll both experience the same force. But the car with more mass or more inertia will move less or have less acceleration because it has more mass. They experience the same force, but the car that has more mass will accelerate less. It's a balance of Newton's second law. So, oh look, we both hit each other with 9,000 newtons, but I have more mass. Well, I'm going to experience less of an acceleration, which is good because then I won't experience that force. Okay, flip over to the back. That is Newton's third law. As you can see, it's very straightforward and simple. For every pair or every force, there's an equal and opposite force acting with it. So, force due to gravity. I just want to reiterate this. We've talked about it in class. I've had you take notes on it previously, but I want to go over it again because this is really, really important because students, for some reason, screw this up a lot. Gravity is a force. Remember, forces cause acceleration. That's Newton's second law in a nutshell. Why? Because think about it. Newton's law is, hey, my unbalanced force causes my mass to accelerate. Interesting. Well, on Earth, I know the acceleration due to gravity is negative 9.8 meters per second squared, and this is assuming positive's up, which means that my force due to gravity, according to Newton's second law, is just my mass times my acceleration due to gravity, which, remember, as I talked about, is my weight. And as I stated, please star this, underline it, circle it, write it in a different color, circle again, italicize it if you can, write it in a different color. Weight equals your force due to gravity, which means when you're figuring out your weight, you multiply your mass times your acceleration due to gravity. When they say, hey, a weight of a student is approximately 600 newtons, or the mass of the student is 60 kilograms, what is its weight? Well, if you want its weight, you multiply its mass, which is 60 kilograms, times 9.8, and you get approximately 600 newtons. So that's the key thing here, is you have newtons equals kilograms times meters per second squared. So please remember, weight is your force due to gravity. They are one and the same thing. So this also means that we can find the force of gravity if we know the mass, or we can find the mass if we know the force due to gravity. We can also find, and I list it here, if we know the force due to gravity and its mass, we can find its acceleration due to gravity. Another word for acceleration due to gravity that they'll call is, what was the word that the Regents uses? It's like a weird one. I'll get back to you on that one. I forgot it off the top of my head right now. But they use like a weird word where they say what's the acceleration, but I'll explain it later. I'll show you when it comes up. I apologize for mentioning it here. Just be aware of it when it comes. So as promised, here's an example in the notes where if you do this, I want you to calculate the object's mass. It's obviously on Earth. So using Newton's second law, please figure out the object's mass. And then lastly, I just want to go back over into Newton's first law, where this is just a reminder. I didn't get to really answer this last time, but when the net force equals 0 newtons, the object will do either of two things. It will stay at rest or move in a constant straight line speed or a constant velocity. So remember, that's when we're in equilibrium. So this brings us to the end of Newton's law notes. I will see you Thursday with these.